So we will continue our discussion on decomposition algorithm. Just to recall what we have discussed so far, right? So we have a gap in between discussing the project. Remember, we first started talking about Bender's decomposition, right? So in Bender's decomposition, remember the motivating application is a so-called News-Bender problem, where you have the first stage decision and the second stage decision. And Bender's decomposition, what we call it, it has a so-called complicating variable, right? Once you fix the first stage decision, then you can solve the rest of the problem by scenario. And then at each iteration, you are taking the dual of the second stage problem, and each of the cut you add either correspond to an extreme point of the dual or an extreme ray of the dual, right? So that's problem with complicating variables. And then we talk about Danzig-Wolff decomposition, right? So we remember in Danzig-Wolff decomposition, we have complicating constraints, right? So we wrote out the complicating constraint as the convex combination of extreme point and plus the Corny combination of extreme rays. And in each of the iteration, what we solve is a so-called pricing problem, right? We need to decide which column we are going to add to the Danzig-Wolff master problem. So recall how the pricing problem are solved is that you get the reduced cost from the master problem, and then you try to generate a column that minimizes the reduced cost, right? So that column can help you, further minimize the cost of the master problem. Okay, so that's an intuition of the Danzig-Wolff decomposition. So today we will talk about Lagrangian relaxation and Lagrangian decomposition. The intuition is very similar to Danzig-Wolff decomposition. They are usually used to solve problems with complicating constraints. But we will show that Lagrangian relaxation can be seen as the dual of Danzig-Wolff decomposition. You will see that in this lecture. Yeah, so recall this is a problem with complicating constraints. Let's assume you have a number of different variables, x1 all the way to xt. All those blocks are decomposable except this single complicating constraints here, right? So in the previous lecture, what we showed that this problem can be solved by Danzig-Wolff decomposition. The Danzig-Wolff master problem essentially only involves these constraints. Instead of writing the problem in terms of x, you write problem in terms of the lambda and the mu, right? So those are the coefficients of those convex combination and Corny combination. And each iteration, you generate a column from those subproblem, right? So you generate an extreme point or an extreme ray of this subproblem. Lagrangian relaxation is targeting the problem with similar structure. You have complicating variables here. So the other way to decompose the problem is just saying, so if we can relax this particular constraint, then the rest of the problem can be decomposable, right? So let's assume if you don't have this constraint, then the problem is decomposed by xi, basically, right? You can write it out as minimize ci transpose xi subject to fi xi equals to bi and xi greater than or equal to 0. Okay, so let's show some motivating application. Maybe let's continue using the motivating application of two-stage stochastic programming to motivate Lagrangian relaxation. So here, just to recall the formulation of a two-stage stochastic programming, we have x as the first stage variables and y omega as the second stage variable in a given scenario omega, right? So in the News-Bender problem, the first stage decisions are the number of newspaper the news vendor buy from the publisher. Then the second stage decisions are depending on the demand of the customer at each of the demand scenario, how many newspaper you are able to sell and how many newspapers you are going to return to the publisher. Okay, and then we talk about how to solve this problem using Bender's decomposition, right? Basically, you fix x, and then you can solve the rest of the problem using the Bender's decomposition, adding those cutting planes. Well, there's another way to look at this problem. The idea is to say, let's translate this problem from a problem with complicating variables to a problem with complicating constraints. So the idea is to say, let's duplicate x for each scenario, right? So let's say if you have 10 scenarios, but you have a single first stage variable, right? But now the idea is to say, let's duplicate the x variables for each scenario x omega here. Well, this is problematic if you just duplicate x for each scenario, right? Because we want a unique first stage decision, right? The news vendor should decide how many newspaper he or she is going to buy in the first stage. It's a unique decision. You cannot make decisions for each scenario separately. So in order to do that, we have to add some constraints. These constraints in the literature, they are called the non-anticipativity constraints, right? So in other words, a news vendor cannot really anticipate the demand of the customer at the beginning, right? So in order to express that, we add those non-anticipativity constraints, saying that all the first stage decisions you made for each scenario must be equal. So here the NACs we add are the first scenario has to be equal to the second one, then the first one equal to the third one, and so forth. The first one has to be equal to the last scenario. Essentially, all the scenarios, the decisions you made for each scenario are equal to the first scenario. Right? That's what the NAC does. Okay. So with that, you can see the structure of the problem will be changed a little bit. Okay, here there is a typo here, so it should be x omega. Right? So we have first stage constraints for each scenario omega, right? And then we have to make sure the first stage decisions are non-anticipative, right? So we add those NACs. And similarly, you just write all the constraints for each scenario omega. So we should add this x omega here. Okay. So with that, let's write down the form of those constraints. You will see that the constraints form now change a little bit, right? So, the complicating variables are disappeared already, right? Because we duplicate the x omega for each scenario, so each scenario got separated. But now we have some complicating constraints, which are those non-anticipativity constraints we just added. Right? So with this very simple reformulation, you can transform a problem from a complicating variable to a problem with complicating constraints. Okay, is this reformulation clear? Here? Yes?
So if we have discrete values of omega, then we can do that. What if we have continuous domain for omega?
Yeah, so we only talk about discrete omega here, right? We don't talk about continuous for this lecture. Yeah. Any other questions here? Okay. Yeah. So if you bet that, you can see that now if we relax those NACs, then the problem can be decomposable, right? So in Lagrangian relaxation, it will propose to so-called dualize the non-anticipativity constraints. Yeah, so here's this application. Let's talk about a toy problem to motivate Lagrangian relaxation again. Okay, so this is so-called a generalized assignment problem, right? So remember in scheduling, we talk about how do you assign jobs to machines, right? This is not a scheduling problem. It is just a very simple assignment problem, right? You just want to assign some jobs to some machines, and the machines have some capacity constraints. It cannot process maybe not all the jobs. So we have some x variables. So xij represents whether you are going to assign job j to a machine I. Right? So xij equals to 1 if you decide to assign job j to machine I. And then each of the machine I has a capacity constraint, right? So if you sum over aij times xij, you can think about the aij as for example, the resource, or usually in scheduling problem, the resource would be the processing time consumed by job J if assigned to machine I. Right? Or the capacity of machine I that job J will consume. So then if you sum over all the machines that are assigned to a given, all the jobs that are assigned to a given machine I, it has to be less than or equal to BI is a capacity of machine I. Right? And then this constraint is saying that each job must be assigned to one of the machines, right? So if you sum over all the I is the index for the machines, right? If you sum over all the machines, the job J must be assigned to one of the machine. Right? So this is kind of like an assignment constraint, and then this constraint is like a capacity constraint. Okay, and in the objective, we are minimizing the total cost of processing all the jobs, right? So if you can, you assume that if you assign job J to machine I, it will incur a fixed cost Cij. Then you want to minimize the summation of all the fixed costs to assign job J to machine I. Okay, so this is a very simple problem with one assignment constraint and one capacity constraint for right. So one of the ways we can solve this problem in a much simpler way is if you treat those assignment constraints as the complicating constraint. Let's see what happens with that, right? So if we multiply all these assignment constraints by lambda j. So lambda j is like a Lagrangian multiplier. You multiply a constraint with Lagrangian multiplier, you can take it to the objective function, right? So this term is basically you are taking all those assignment constraints to the objective function by so-called dualizing this constraint, right? So you can just believe me, you can dualize those constraints and get a pretty decent Lagrangian bound. Then later on we will talk about the theory of Lagrangian, right? So this is just to give you a feeling, right? If you dualize some constraints, you might get an easier problem, right? So let's say if we you just relax those constraints through something called Lagrangian relaxation. What it does is you multiply each of these constraints by a Lagrangian multiplier lambda j, and then you are left with this problem, which only has those capacity constraints for each of the machine I. Okay. Now, as you can see, with the dualizing this constraint, the rest of the problem is like a knapsack problem again. So you can think about each machine is like a knapsack. The capacity of the atom you packed into this machine has to be less than or equal to the machine's capacity, right? And the objective is a linear objective function of those xij's. Okay. And now, if you analyze it a little bit further, you will find out that the rest of the problem, after dualizing the problem, after dualizing those assignment constraints, the rest of the problem is decomposable by each machine I. Okay, so if you, this is just a rewrite of the objective. Here's all the constraints for each of the machine I. So as you can see in the objective, here there is a summation over I, right? And for each summation, each of the summation over I term, there is a summation over j. So as you can see, the problem can be easily decomposed by machine I, which you get rid of the summation over I, and you just keep the constraint for machine I, right? So each of the machine is like a separate knapsack problem, right? So if you do the Lagrangian relaxation, so as you can see here. Let's say each machine I involves a separate knapsack problem. Yeah, so as you can see, when you dualize some of the constraints, then the problem becomes decomposable. Then you can solve each of the knapsack problems separately, right, which is much faster than solving the original problem. Okay, so here's the intuition of why we are doing Lagrangian relaxation. Okay. Any questions regarding this application here? Okay. Yeah, so far we just want to give you some intuition why we want to use Lagrangian relaxation. Right? Usually the application in practice is that if you remove some of the complicating constraints, then the rest of the problem can be solved easily. Right? Usually what we mean by solved easily is that the rest problem can be decomposed into some subproblem. Right? Then you can leverage your parallel computer to assign each of the subproblem to a single thread. Okay, so that's what usually happens. So now let's start talking about how we are going to do Lagrangian relaxation. So this lecture is closely connected to Lagrangian dual we have studied before, right? But we want to apply Lagrangian dual to problem with integer constraint as well, not just to convex continuous problem. So without loss of generality, let's consider the following MILP problem. Okay, so we have C transpose X, which is a linear objective function, and then we have two sets of linear constraints. So you can assume AX less than or equal to B is a bunch of linear constraints, and EX less than or equal to D is another set of linear constraints. And here we have X belongs to this set capital X, where the set capital X are basically saying some of the variables from 1 to P has to be binary variables, and then the rest of the variables are greater than or equal to 0. In other words, the X variables are mixed binary. Right? Some of them are binary, some of them are non-negative continuous variables. Okay, so without any loss of generality, let's just think about this AX less than or equal to B as the complicating constraints, right? So in our previous example, the complicating constraints are in the two-stage stochastic programming setting, the AX less than or equal to B are the non-anticipativity constraints, right? If you remove those, they can be, the rest of the problem are easy to solve. And in the second problem, in the generalized assignment problem, those are the assignment constraint in the second example. Right. And then we treat this EX less than or equal to D as the so-called easy constraints. For example, those constraints can be some constraints with decomposable structure. Right? So in the two-stage stochastic programming setting, those constraints are the constraints for each scenario separately. Right? They are decomposable. And in the knapsack problem, the EX less than or equal to D are representing those knapsack constraints. Okay. Is the setting clear here? Okay. Yeah, again, then the idea of Lagrangian relaxation is the following. We would like to dualize the complicating constraints, right? In other words, if you before you think about dualize, you can think about a way of let's remove the complicating constraint. Then the problem is easy to solve, right? But just removing the constraint is a little bit too trivial. You can think about removing the constraint as having a Lagrangian multiplier of 0. Right? So if, let's say, if lambda equals to 0, it is equivalent to removing the constraints. Right? So this will give you a lower bound as well, right? Because you just remove some of the constraints and you are minimizing, then it will give you a lower bound, right? But this lower bound might be too loose. So you, in terms of the Lagrangian relaxation, right? We talk about Lagrangian dual. Usually you dualize some constraints, then you want to get the strongest possible bound you can get, right? Okay. And then in order to get a valid lower bound, we need the lambda has to be greater than or equal to 0. Right? So we've studied Lagrangian dual before. You guys have derived KKT conditions for some of those continuous problems. You know that since ax less than equal to b is less than or equal to 0, then you want to multiply it with some positive Lagrangian or non-negative Lagrangian multiplier such that this d lambda function give you a lower bound of the original problem, right? And recall that in the past we have proved before that for any of the lambda greater than or equal to 0, the d lambda function is a lower bound of the original problem, right? So it is a very simple argument. You can check, any feasible solution to the original problem will give you, if you plug it into the d lambda, it will give you a lower bound than the original objective. And the optimal solution is a feasible solution. So if you plug in the optimal solution, it will give you a lower bound. And this is just a few lines of proof here. Okay. And the Lagrangian dual is defined as follows. You are trying to get the tightest lower bound possible, right? So we talk about for any of the lambda greater than or equal to 0, the d lambda function will give you a lower bound, right? And you want the tightest lower bound possible, which is you want to maximize over lambda greater than or equal to 0 such that this V Lagrangian relaxation give you the tightest lower bound possible. And we know that for convex problem, right? If you have convex problem, strong duality hold under some regularity conditions. Here you can just assume strong duality hold. And we have the Lagrangian relaxation is equal to the value of the Lagrangian relaxation is equal to the original problem, right? For convex problem. And for linear program, of course, you have a linear programming strong duality, right? Another question we want to ask in this lecture is that what if the problem is non-convex? So we are talking about mixed integer linear programming problem, right? The MILPs are non-convex problem. So what is the relationship between the Lagrangian relaxation bound and the original problem? So in general, we have the Lagrangian relaxation bound is less than or equal to the original problem. And for some of the problem, you can see that there is a so-called duality gap. Even if you take the tightest Lagrangian dual bound, you are not going to get the value of the original problem. So we will show that in this lecture. But maybe pause here to say if the definition of the Lagrangian relaxation is clear. You dualize a complicating constraint, which gave you a lower bound, and then the Lagrangian relaxation is to find the tightest lower bound possible from this dualization. Yes?
Can your complicating constraint be an equality constraint?
Yeah, it can be, right? So if you write ax less than or equal to b, if you have equality constraint, you just write ax less than or equal to b, and then ax minus ax less than or equal to minus b. Right, so it's equivalent.
Okay.
Right.
So you'd have two then.
Just write two sides of the equality.
Okay.
Right. Yeah. So without loss of generality, you can just assume that we only have inequality constraints.
Okay.
Yeah.
So in that case, though, you'd have you have two complicated constraints. Then.
Yeah. Because we just want to simplify the notation a little bit. In terms of if you look at the first two applications we talk about, right, the NACs are equality constraints, and also this assignment constraint are also equality constraints. So in this case, if you dualize for example, this equation here, you can just assume the lambda is a real number, right? Basically, right? If you are dualizing an equality constraint, but then if you dualize an inequality constraint, you assume the lambda is greater than or equal to 0. It's just the same thing as you did when you are taking the dual of a linear program, right? The signs of the dual have to be consistent with the primal constraints, basically. Yeah. Any other questions here? Okay, so in order to answer the question I just raised, right, will the Lagrangian dual give you the same bound as the original problem? So in order to answer this question, there is a very strong theorem people have discovered, which is called the primal characterization of Lagrangian relaxation. The motivation is the following. We want to have a primal characterization of how tight the Lagrangian relaxation is. Right? For example, you want to answer questions such as you know the Lagrangian relaxation is a lower bound, but how does it compare with other relaxations, right? Things like linear programming relaxation. For an MLP problem, solving the linear programming relaxation is very easy, right? But solving the Lagrangian relaxation, as you can imagine, is very hard, right? You are trying to find the optimal dual. Here's a theorem that describes how tight the Lagrangian relaxation is in terms of the relaxation of the primal problem, right? Because if you directly look at Lagrangian relaxation, it involves a max-min problem. It's very hard to get an intuition of how tight that bound is. But there is a theorem which gives you how tight the Lagrangian relaxation is in terms of the primal problem. So let's look at it very slowly. So this theorem says the value of the Lagrangian relaxation is equal to the following optimization problem. Right? So let's look at it very slowly. It has the same objective function, C transpose X, right? And the linear constraints are the same. It also keeps the complicating linear constraint. But the last part is saying that, originally I have those, inequality constraint, and I also have, remember X belongs to capital X means X are mixed integer variables, right? So this is saying that I'm giving you the convex hull of the set that involves the inequality constraints, the non-complicating inequality constraint, and the integer constraints. Okay, so essentially it is taking the convex hull of the constraints that you did not dualize during Lagrangian relaxation. Okay, so recall that in Lagrangian relaxation, we are dualizing those complicating constraints, right? So after you dualize those complicating constraints, the rest of the constraints are these two constraints, right? Involve the linear constraints that you did not dualize and the integer constraints, right? So this is saying that when you do the Lagrangian relaxation, you get the same bound as the convex hull of those constraints you did not dualize intersect with the constraint you dualized. Okay. Yeah.
So I just got a little confused.
Yeah, go ahead. Yeah. Mm-hmm.
So is the convexified X is going to have a continuous variable, or is it?
Say that again.
Is the convexified X on the VLR the continuous variable X, or?
Yeah. So this set, maybe this set capital X, is the following. Let's go back again, such that you guys are familiar with the notation. So this set capital X is saying that, X has some binary variables, and then the rest of the X are continuous variables. So this capital X, you can think about the capital X essentially represent the integer constraints in the problem. Right? So this represents the integer constraint in the problem. So this is when you do the Lagrangian dual, recall that we are dualizing those AX less than or equal to B. Those are the complicating constraint. And the rest of the constraints are, let's call this EX less than or equal to D, the so-called non-complicating constraints, right? You are still solving this problem with EX less than or equal to D. And X belongs to capital X represent the integrality constraints. Okay, so those two constraints are the constraints you did not dualize when you calculate the Lagrangian dual. Okay, they are left in the constraints. Okay, then this theorem is saying that the Lagrangian relaxation will give you the following. You keep the objective, and then X has to be in the convex hull of the constraint you haven't dualized, intersect with the linear constraints you dualized. Okay. Yes, I will show you a picture to explain that later. But before showing the picture, maybe let's pause here to see if people have any questions with the notation here. Or maybe I can ask a question. With this primal characterization, can you show that the Lagrangian relaxation is weaker than the original problem? Or maybe can you show that this is stronger than the LP relaxation? Okay, so maybe I get you more confused. So if you remember what we talked about before, right? So this is a bound of the Lagrangian relaxation. If you think about the the value of the original problem, it is essentially minimizing x C transpose x subject to all the three constraints. Right, so this is the original problem, right? And we've studied before that, when you are minimizing a linear function over a non-convex set, right? So this feasible region is a non-convex set because it is a mixed integer linear programming problem, right? So we are minimizing a linear function over a non-convex set. It is equal to minimizing the linear function over the convex hull of this non-convex set. This is a theorem we talked about before. If maybe people don't remember that, but we can repeat that. So then VP is equals to minimize x C transpose x subject to the convex hull of the feasible region. Okay. So this is essentially saying that, the original problem have these three sets of constraints, right? And if the function is linear, we talked about this before in the integer programming lecture. If you forgot about that, you can go back to the integer programming lecture and revisit that theorem. We did not talk about how to prove that. But if you have a linear function over this non-convex set, it is equal to the same linear objective over the convex hull of this the same non-convex set. Okay. So that's a theorem we talked about before. Right? You can take the convex, this represents the convex hull of the set X such that X satisfy these three constraints. Okay, so now let's compare VP with V Lagrangian relaxation here. Right? So recall that VP is minimizing the linear function over the convex hull of all the constraints. But VLR is saying that I'm only convexifying some of the constraints here, right? Instead of I'm convexifying all the three sets of constraints simultaneously, right? So you can view Lagrangian relaxation's value as a partial convexification of the constraint sets, right? It only take the constraint you did not dualize to get the convex hull. And then you have to intersect the convex hull with the linear constraints you dualize. And in other words, if you do not dualize any constraint, you get the original problem, right? So this AX less than equal to B is, there are no constraints you dualize. Then in the extreme case, you can show that the Lagrangian relaxation is equal to the original problem. The more constraints you dualize, you are going to get a much weaker bound, right? Since you are partially convexifying the constraint that you did not dualize. So that's some intuition here. Yeah, so that's why I say here is that Lagrangian relaxation provides the same bound as like a partial convexification of the feasible region. Right? You only convexify the feasible region described by the constraint you did not dualize. Okay? And this is true in general for any non-convex set X. Even though X is like a nonlinear feasible region, this is also true. I remember I tried to prove that before. Yeah, go ahead.
So the objective function for the Lagrangian relaxation then, why doesn't it have the multiplier with the, I guess, the AX minus B term?
Oh, you mean yeah, so that's why we call it a primal characterization. Right?
Okay.
It doesn't have to do with the dual. So you want to get a characterization of how strong the Lagrangian dual is without the dual variables.
Okay.
Right? That's a motivation why we want to get this characterization. Right? So because with the dual variable, you still have to characterize what are the optimal dual variables and so forth. It's very hard to intuitively view how strong this bound is, right? So the idea of the primal characterization is to say, I don't care about what the optimal dual variable is. I just show you in terms of the primal variables how strong this Lagrangian relaxation is. Okay. Yeah. Okay, so we will show a proof of this for MILP representable constraints. And you can show actually this is in general true for any non-convex set X. Yeah, so any more questions related to this claim here? The definition of this claim, not the proof, of course. Okay, so maybe before we show the proof, let's say if I have a picture. Okay, so let's show a geometric intuition of the primal characterization of Lagrangian relaxation. Okay. So let's first look at this problem, and then let's look at where is the value of the LP relaxation, right? So let's assume we are trying to minimize this z variable, right? We try to go up since we are minimizing the z here, right? And the linear constraints are the following, right? So this Ex less than equal to D describe this polyhedral set here, right? And the Ax less than equal to B, we assume it is the complicating constraint. It describes this polyhedral set here, right? And the intersection of these two constraints are the linear relaxation, right? So it is essentially the intersection of the polyhedral is this particular region here, right? Hopefully that's clear. And the optimal value is obtained at an extreme point of the intersection, right? So here, since we are minimizing z, the optimal value of the LP relaxation is obtained at this point here, right? And hopefully that's clear. Okay, so how strong is the Lagrangian relaxation? The Lagrangian relaxation is a convex Hall. So this set convex Hall of S, is describing the convex Hall of the feasible region described by the constraint you did not relax. Right? So we already relaxed this part of the constraint in the Lagrangian relaxation. Right? So the rest of the constraints are those inequality constraint and the integrality constraints. Right? So supposedly, those red points are the integer points in this linear constraint that you did not dualize. Then the convex Hall of the feasible region describing by the constraint you did not dualize is this region here. Right, so those are the convex Hall of the integer points you did not dualize, okay? And then the Lagrangian relaxation is saying I'm taking the convex Hall here, intersect with Ax less than or equal to B, right? So then that region is, okay, maybe let's draw it using some color here. So this purple region is the feasible region of the primal characterization, right? So it's a convex hull of the constraints you did not dualize intersect with the constraint you dualize. And maybe let's draw with a different color. And then the feasible region of the LP relaxation is this region here, right? You just intersect two polyhedral sets. Okay. Yeah. Then as you can see, the optimal solution in the primal characterization of the Lagrangian relaxation is obtained at one extreme point of this purple region, right, which is this point. Of course, it gives you a tighter relaxation than the original problem, than the LP relaxation, yeah.
Why aren't only the integer points feasible for the Lagrangian relaxation?
Well,
Is the integrality constraint
yeah.
not?
Yeah, so then why are the integer points feasible?
Why aren't only the integer points feasible? I guess.
Yeah, so recall that in the Lagrangian relaxation, the primal characterization, right? You are taking essentially AX less than or equal to B intersect with the convex hull of the constraint. So this set X is described by EX less than or equal to D and X are integer, right? So let's check what this convex hull of this set is, right? So this set are the linear constraint, which is this polyhedral set here, right? And this is saying that I'm taking the convex hull of the integer points in the left polyhedral, right? Which are the convex hull of the integer points in the left polyhedral only, which is this region here, right? And this region intersected with AX less than or equal to B is this purple region I draw here, right? And this purple region is smaller than the green region, right? The green region is a linear programming relaxation, right? So we should say, so green is the LP relaxation, and the purple region is the LR, Lagrangian relaxation. Okay. And the Lagrangian relaxation still doesn't give you the optimal solution to the original problem because you are intersecting with a partial convexification with the original problem, right? And as you can see, this point is not an integer feasible point since you are partially convexifying the some of the regions here. And as you can see, the optimal solution is obtained at this red point here, which gives you an even lower solution. This should be higher objective than the Lagrangian relaxation. Okay, so that gives you some geometric intuition on, the Lagrangian relaxation is tighter than the LP relaxation, but it still does not give you an integer feasible solution. Okay, so that's a geometric intuition of this problem. So how do we prove this theorem? Okay, so to prove this theorem, you need a couple of things. First is this Mayer's theorem, right? So if you want to remember a theorem in integer programming, this is one of the things. It's just like the Minkowski theorem in linear programming. You should remember the Mayer's theorem is like a theorem in integer programming. You should remember, which is given a rational matrix E and a rational vector D, right? So let's assume this is the set of the constraint that you did not dualize, and X is a mixed integer region here. And it basically says the convex hull of an MILP constraint is a polyhedral set. Right? So this is saying that there exists a rational matrix H and rational vector H such that the convex hull of this constraint can be described by a polyhedral set. Right? Intuitively, this is true, right? You draw the, for example, you draw the convex hull here. It is clearly a polyhedral representable set. Okay, so we will use this Mayer's theorem in the proof. I'm not going to the details here, but essentially these rely on linear programming duality. So you can try to take the dual yourself to check the proof here. So first of all, let's write down the result of the primal characterization. It's essentially the complicating constraint, and also X is in the convex hull. Let's use S to determine the feasible region of the constraint you did not dualize, right? And according to Mayer's theorem, there exists some constraint H and capital H and small h, such that this convex hull can be described by some polyhedral constraints. So now we have this problem P tilde, right? We just want to prove that this problem P tilde equals to the Lagrangian relaxation. The way you do it is you first take the dual of this linear programming problem, right? So this is essentially a linear programming problem. I'm relatively confident you guys are comfortable taking the dual now. So you can take the dual of this min problem will become a max problem. And then you can separate the Lagrangian multiplier lambda and the mu, which is the other side of the dual variable. So you can kind of separate these two problems since you are maximizing them. At the same time, you can think about this as an outer problem to maximize lambda and the inner problem to maximize mu. And you take the dual of this inner problem, you essentially kind of reproduce the original primal constraint, right? And since we know that hx less than or equal to h describe the convex hull of the the region you did not dualize, then it is equal to the original constraint, and x is a mixed integer. So that's a trick. You take the dual twice to prove that. And basically here you essentially this is nothing but the Lagrangian relaxation. Okay, so you can take a look at it in detail after class. Okay, so now that you hopefully this intuition at least is clear for you, right? And then you know when you apply Lagrangian relaxation, you are going to get something tighter than the LP relaxation, but still that doesn't give you the optimal value of the original MILP. Right? So this is a key takeaway of what this theorem implies. And then the next question we want to answer is that, how do you get the Lagrangian dual? Right? We already defined what the Lagrangian dual is, but how do you calculate the Lagrangian dual? So for some of the problem, it's relatively easy, right? We had a lecture on Lagrangian dual in the past. For some problem like QCQP, we have this problem in the exam as well, right? What is the Lagrangian dual of a QCQP, right? It has a closed form solution. Basically, you can write out the Lagrangian dual function d of lambda in a closed form. Right? You can derive that for the QCQP using some basic linear algebra. And then we show that the dual problem is essentially equivalent to an SDP from the Scher's lemma. That's what we showed before, right? So for some of the convex problem, this problem may not be convex, but still the Lagrangian dual can be written as an SDP. So for some of the problem, it's quite easy to get the Lagrangian dual as a convex problem. But for some other problem, it's not so trivial, right? So if we have an MILP, right? So essentially, you can think about this d lambda function as a value function of an MILP, right? So if you are given a lambda value, you have to solve an MILP to determine what the value of d lambda is, right? There is no closed form solution of an MILP, right? If there is a closed form solution, life will be too easy, right? You give a lambda, it will output the objective value of an MILP. There are ways to do that, but that's very expensive, right? So you can think about the d lambda essentially involves solving an MILP problem, right? I gave you a random value of lambda, then you have to solve this MILP with respect to x to get the value of d lambda, right? So in other words, there's no closed form solution for this d lambda. Each time you solve an MILP. So in this case, we need an iterative algorithm to find the lambda that maximizes this function d of lambda, right? Okay. So this is not a very, very easy problem to solve. First of all, we need to analyze what is the property of lambda, right? D lambda. So as you can see here, this maximization problem over lambda greater than or equal to 0, it is almost like an unconstrained optimization problem, right? So you have lambda greater than or equal to 0, but you can always do a line search to keep lambda to be greater than or equal to 0. So this is essentially like an unconstrained optimization problem. You don't have many constraints on the lambda, right? So if this d lambda has very nice property, for example, if d lambda is convex and continuous and differentiable, then this problem is really easy, right? In the third lecture, we talk about unconstrained optimization problem, right? So if this d lambda has very nice property, then getting the Lagrangian dual is not that hard, right? You can even do a gradient descent if d lambda is differentiable and convex. Or in this case, it should be concave, right? So if I'm maximizing, if d lambda is a concave function, then this problem is very easy. You can do like a gradient ascent to find the optimal value of d lambda, right? Then life would be very nice if this d lambda is concave and differentiable. So let's check what is d lambda's property especially when the feasible region is described by an MILP. So a property here is the following. It has some nice property and some not so nice property, right? Essentially, when the problem is an MILP, we know that d lambda is a concave function, which is nice, right? You want to if you can maximize over a concave function, maximize over a concave function is equivalent to minimize a convex function, right? So it's essentially a convex problem. And d lambda is also continuous. That's a nice property. For an MILP problem, we will show that d lambda is a piecewise linear function. Okay. By piecewise linear function, it means it's like for example, if you have this absolute value function, it is piecewise linear, right? Each piece of this function is a linear function, but at some point you will have a breakpoint which will change the slope of this piecewise linear function. But this function d lambda is not differentiable everywhere. So this is called a non-smooth function, right? If you have a function whose first order derivative is continuous, then this is a smooth function. But the d lambda is a non-smooth function, right? So for example, what is a non-smooth function? Again, this absolute value function, if you think about this function x, which is, let's say fx is the absolute value of x, right? So when x is greater than or equal to 0, this is fx equals to x, and then when fx is less than when x is less than or equal to 0, fx equals to minus x, right? So if you take any point on this function, for example, if you take a point here on this function, it is differentiable, right? The derivative equals to 1. And then if you take a point here, the derivative is minus 1, right? But if you think about this point as x equal to 0, you don't get a derivative here, right? If you consider an absolute value function, it is non-differentiable at the point x equals to 0. That's what the simplest example of a non-smooth function. Okay. So how do we prove that d lambda has those properties? So here we have a quite straightforward proof here. Okay. So essentially you can apply the so-called Mayer's theorem, right? So by definition, d lambda is minimize x over this MILP region, right? And we know that this is equivalent to minimize the convex hull of the feasible region. And also we know that by Mayer's theorem, so from here to here, it is Mayer's theorem. The convex hull can be described by those linear constraints. right? So here, so if the constraints are linear, they are minimizing over, a linear function as well, right? Then the optimum always obtained at one of the extreme points, right? Let's assume this problem is bounded, right? So this is a polyhedral set, and here we have a linear objective. Then this is equal to minimizing over all the extreme points of the polyhedral set. Okay, so where K is a set of extreme points for the polyhedral set Hx less than or equal to H. Okay. Okay, so now as you can see here, d lambda essentially is taking the minimum of a bunch of linear functions with respect to lambda, right? So here, K are a set of finite extreme points. So you can think about d lambda as taking the minimum of a bunch of linear functions. And intuitively, here's how d lambda look like, right? So let's assume you have those three linear functions, and d lambda is taking the minimum of those three linear functions at each point. Right, so if you take the minimum of these three linear functions, it is essentially at each point so at this point the minimum of this is this function, and then here the minimum becomes the second function, and then in this breakpoint the minimum is at the third function. Right, so the minimum of those three linear functions is essentially a piecewise linear function. Right, and since you are taking the minimum of a finite number of functions, the d lambda will be a concave function. Right? So we already showed that the maximum of a bunch of convex function is concave, then the minimum of a bunch of concave function is also concave. Okay? So that proves the property here. Okay, so then now we know d lambda is a non-smooth concave function. We need some algorithm to solve this problem. Right? How do you optimize d lambda when it is a non-smooth concave function? Right? The tricky thing here is that it is non-smooth. If it is a smooth function, you can use gradient descent or Newton's method or whatever. Right? But when it is non-smooth, you cannot use gradient descent because at some points it does not have a gradient. Right? Yeah. And then the two most basic algorithms are so-called the cutting plane method and the subgradient method. We will only talk about these two most basic algorithms to solve this non-smooth convex problem. So let's first talk about the cutting plane method. So let's first do a very naive reformulation of the problem d lambda, right? So recall that the d lambda essentially it is taking the minimum over the number of a number of linear functions, right? So each of the linear functions correspond to an extreme point of its feasible region, right? So you probably have seen this before in Bender's reformulation, right? So if you let eta to be less than or equal to each of these linear functions correspond to the extreme points, then in the objective you are maximizing over eta. Then essentially eta will be obtained as the minimum of all those linear functions. Basically, this is a reformulation of d lambda. Okay, and we already showed this in Bender's reformulation. So recall that K is a set of all the extreme points of the convex hull. So the issue with this reformulation is that you cannot enumerate all the extreme points, right? It's just in the Bender's decomposition or in column generation, you cannot afford to enumerate all the extreme points, right? And recall what we did in the past is that when you cannot enumerate all the extreme points, you start with a subset of extreme points, and you gradually generate the extreme points on the fly, right? When you find out that a given cutting plane is violated, you add them back, right? And similarly, in the column generation, what we did is that you start with a subset of columns, and you gradually generate the column that give you the minimum reduced cost. That's what we did before. And similarly, we can do exactly the same thing here, right? We start with a subset of extreme points, right? So then you form a so-called Lagrangian master problem with, that's denote the subset of extreme point as capital K naught, right? So K naught is a subset of those cutting planes, right? If you add all the extreme points, it's equivalent to the original problem. Then if you have a subset, then it is a relaxation. So what you can do is you solve this Lagrangian master problem. It will give you a solution, eta naught and lambda naught, right? Let's denote this as the optimal solution to this Lagrangian master problem. Then the next step is to find the extreme point corresponding to the maximum violation, right? So we are relaxing the constraint by adding a subset of cutting planes, right? Now you get a solution. It may not satisfy all the cutting plane corresponding to all the extreme points, right? Then you need to find the cutting plane that are most violated, right? It's similarly to the column generation. You are finding the column that give you the minimum reduced cost, right? So this is finding the constraint that are most violated. So how do you find the constraint that are most violated, right? So essentially, the thing we are solving is we have a solution lambda naught and eta naught, and we want to check among all the extreme points which one it mostly violated, right? So one of the naive way is that you enumerate over all the extreme points, right? And of course, we are not going to do that. This is equivalent to just solve the problem with the constraints, right? It's similar to the column generation. You also want to enumerate all the extreme points, but you didn't do that. You just solve a pricing problem to generate the column that give you the minimum reduced cost, right? So what you do is you solve the problem that give you the maximum violation of the constraint, which is essentially this problem here. This is called the Lagrangian subproblem here. Okay. And if this problem is decomposable, let's say if these constraints are decomposable, then this Lagrangian subproblem is decomposable as well, right? So the Lagrangian subproblem is an MLP, and it can be decomposable. Okay, so this is a key to the the Lagrangian master problem and subproblem. Okay, let's pause here a little bit to see if people have any questions. Okay, so maybe let's repeat going back a little bit, right? Okay, so let's first start from here, right? The d lambda function is like enumerating over, all the extreme points of the feasible region, right? So at least I guess most people can see that, right? And then you can reformulate this as the minimum over some linear function. We've talked about this before, right? This is like the d lambda is a minimum over all the three. Let's assume you have three extreme points that correspond to three linear functions. You are taking the minimum of these three linear functions. And this d lambda can be written as the following form, right? You are maximizing over eta, but eta is a minimum of all the linear function, right? So let's say k equals to 3, then you have 3 constraints here, right? So eta is a minimum of those 3 linear functions. But in practice, you don't have only 3 extreme points, right? You can have exponential number of extreme points. So that's why you start with a subset of extreme points, which is k naught, right? K naught is a subset of all extreme points. Usually it is a very small number. And since you are relaxing all the extreme points by a subset of extreme points, you may not satisfy all the constraints, right? So since you remove a huge number of constraints. Then when you find a feasible solution to this relaxed problem, you want to find a constraint that is most violated, right? So you can get a solution from this relaxed problem denoted by eta naught and lambda naught, which may not satisfy all the constraints corresponding to all the extreme points. Then we need to find out that for my current solution, lambda naught, and eta naught, what is the extreme point that are most violated, right? So then you have to solve this particular MILP problem to find out the most violated extreme point, right? So it's, instead of enumerating over all the extreme points, then you just give the feasible region of X, right? So the extreme points are generated from this feasible region. You can just put this feasible region as a constraint. Okay, and so with that will give you the most violated cutting plane, and you add this constraint back to the problem. If you find out that even the most violated constraint is satisfied, then you are done. Right? You can prove that all the constraints are satisfied. Okay. Otherwise, you add the most violated constraint to the master problem, and you keep generating those constraints. Right? You can iterate between the Lagrangian master problem and the Lagrangian subproblem. Okay. Any questions here? Right. Okay, so as you can imagine, this has a very nice connection with Danzig-Wolff decomposition. Because both problems deal with complicating constraints, right? Intuitively, there must be some connections with these two problems. So you can show that the Lagrangian master problem is the LP dual of the Danzig-Wolff master problem, right? So remember that each extreme point in the Danzig-Wolff master problem is a column, right? And here in the Lagrangian master problem, each extreme point is a constraint, right? So there's some duality here. You can show that the Lagrangian master problem is a linear programming duality of the Danzig-Wolff master problem. And the Lagrangian subproblem is essentially the same thing as the pricing problem in Danzig-Wolff decomposition, right? So recall that in Danzig-Wolff decomposition, each iteration, you are trying to generate a column that has the minimum reduced cost, right? So the column corresponding to the minimum reduced cost is essentially the constraint that is most violated in the dual, okay? So you can show that the pricing problem of the Lagrangian subproblem, the pricing problem of Danzig-Wolff is the same thing as the Lagrangian subproblem. Okay, so then there is another method to solve the Lagrangian dual, which is called the subgradient method. Right? So we already said, the d lambda function is not a differentiable function. Right? For a non-differentiable function, it does not have a gradient everywhere. But for a convex non-differentiable function, it has something called a subgradient everywhere. So how do we define a subgradient? Okay. So if you have a function f, then the vector g is a subgradient of f if you have fx greater than or equal to x naught plus g transpose x minus x naught. Okay. So when you look at this formula, it is very similar to the first order characterization of the convex function, right? So the first order characterization of convex function thing is that the gradient will underestimate this function, right? If you have a convex function, this is basically what we did in outer approximation, right? If you take a point here, and then you take the gradient here, then this linearization underestimate the convex function, right? This is what we did in outer approximation and so forth. Okay, so the subgradient is saying, although the function is non-differentiable, I can always find so-called like a subgradient direction G that this fx naught plus G transpose x minus x naught always underestimate the function fx. Okay, so here intuitively always think about this absolute value function. It is a non-differentiable function, non-smooth function, and then it is convex as well. It's very clear to say the absolute value function is convex, right? So what is, of course, it's differentiable at most of the points, but it's non-differentiable at x equals to 0, right? So here the subgradient at x equals to 0 is not a singleton, right? So basically all the values between -1 and 1 is a subgradient at x equals to 0. Why? Because if you draw some arbitrary functions, let's say, of course, this function itself under approximate the absolute value function, right? So if I draw an arbitrary function here, for example, this also underestimate the absolute value function, right? So all the functions with a subgradient -1 to 1 always underestimate this function, right? So the subgradient can take values between -1 and 1, okay? And similarly, for a concave non-smooth function, you can define something called a supergradient, which is that some linear functions that overestimate a given concave function, right? So if you take the minus absolute value function, you can show that very easily that -1 to 1 is a supergradient of this concave function minus absolute value. Okay, and the takeaway here is that subgradients is usually for convex functions and supergradient is for concave functions, right? And we know that the d lambda is a concave function, therefore it must have some supergradient, right? And then what we need to do is that we need to find out at a given point, lambda, what is the supergradient of d lambda, right? If we can find a supergradient of d lambda, we can do something which is similar to gradient descent, but here we don't have the gradient. We can do, subgradient descent or supergradient ascent, right? To maximize a concave function, you can do something like a supergradient ascent, right? Very similar to gradient ascent, but here we only have a supergradient instead of gradient. Okay, so now let's say what we need to do is that at any given point, let's give a very arbitrary point, lambda naught, right? We need to show that what is a supergradient of d lambda at any arbitrary point, lambda naught. Okay, yes?
I still don't understand what subgradient physically means.
Okay, yeah. Physically means you can think about if a function is non-smooth, if the function is smooth, the gradient is like the maximum increase direction, right? But if the function is non-smooth, you don't have that. You only have some directions that underestimate this particular non-smooth function here, and there can be multiple, that's quote gradients that underestimate this non-smooth convex function, right? So here you can try at any point between -1 and 1, it always underestimates this non-smooth function. And the supergradient is to have some quote gradients that overestimate this function. Okay. So if you are lucky, you can, for example, if you go around this subgradient direction, you can also minimize this function. Okay, we are not going to talk about convergence of this sort of things. It has some convergence properties, but not as strong as gradient descent. Okay. Yeah, so essentially for each of these points, lambda greater than or equal to 0, we need to find a supergradient for d lambda 0, right? So recall that this is a problem you are going to solve at a given point, lambda 0, basically an MILP problem. Okay, so this proposition is saying that you solve this MILP at lambda naught and you get the optimal solution as x naught. Then it says this s naught equals to ax naught minus b is a supergradient of this function at lambda naught. Right? So this proposition gives you at least one supergradient at any arbitrary point. Right? So if you take this super gradient, you can do something like a super gradient ascent for the function d lambda. So why this is a super gradient? The proof can be very simple, right? So here essentially, by definition, d lambda is equal to the minimum over all the extreme points, right, of this feasible region here. Okay, so this is a feasible region. It is taking the minimum over all the extreme points. Okay. And then since x naught is the optimal solution of this problem, right? So x naught is one of the extreme points. So you are taking the minimum over all the extreme points, but x naught is one of the extreme points, right? So that's why the minimum over all the extreme points must be less than or equal to a given extreme points. Right? So you just take x naught to be the extreme points here. Then you rearrange this a little bit, right? So you first plus lambda node transpose this term, and then you have to minus it again. So you just rearrange this a little bit. Then if you look at the first few terms, right? Essentially, this is nothing but the value of d lambda naught, right? Because x naught is the optimal value of this MILP when you evaluate it as lambda naught. So now you kind of show that the S naught is a super gradient of d lambda. Okay. Right. So with that, we can do something like a super gradient ascent. Right. We already showed that at a given point lambda naught, you can calculate the super gradient. Then you use the step size mu to search along the direction S naught, right? That's kind of like ascent direction. So what you do in the subgradient method is the following. At a given iteration lambda k, you solve the Lagrangian subproblem d lambda k to get the solution, right? So the solution is xk. The solution xk gives you a super gradient sk equal to axk minus b, where xk is the optimal solution to the Lagrangian subproblem, and then you can update the Lagrangian multiplier by doing, like a gradient ascent step, basically. Okay, and then the question is, how do you choose this step size mu, right? So recall that in gradient descent, we did something called line search, right? You are doing some like a Wolf condition and so forth. But for this subgradient method, usually people don't do line search, especially for MILP problem. The reason is that evaluating this function d lambda is very expensive, right? Each time you evaluate this function, you are solving an MILP, right? So in the past, when you are solving an unconstrained optimization problem, each time you evaluate the function, the function is an algebraic form, right? But here the d lambda involves solving an optimization problem, right? So if you do line search, you have to do a lot of function evaluations that can be very expensive. So people have come up with some heuristics for choosing the step size. I'm not going to the details, but you can read it into more detail. Here, essentially, you choose the step size mu k as this a little bit nasty form, right? So in the denominator, you have the norm squared of the the super gradient, and then the ZU term here is an upper bound you can obtain from a heuristic, and the eta k is essentially the value you got at a particular iteration here. Okay, and the alpha naught is typically chosen between 0 and 2, and is reduced by multiplying a given number if it fails to improve for a number of iterations. Right? If you keep doing line search using a particular step size, and it doesn't improve, that means you are overshooting your step size, right? So that means you should shrink your step size. Right? So what they do is that if you use this alpha that is too large, then you can multiply alpha by a given value beta, which is between 0 and 1, then you can shrink your step size in the next iteration. Okay, that's just a heuristic way of choosing the step size. Okay. So I think I'm a little bit over time. Let's talk about the rest maybe in the next lecture.